In this lecture, we are going to discuss about the quadrature amplitude modulations. Why the name quadrature? Because we are using two carriers and each of them they are quadrature to each other. Like one we are using cos omega ct and the quadrature of cos is the sine. So that is why the name is quadrature amplitude modulations. So we have already discussed the amplitude modulations in very detail in our previous lectures. The mean of amplitude modulation is that changing the amplitude of the carrier signal in accordance with the message signal. So let's start the quadrature amplitude modulation. So we will discuss both transmitter and receiver. So let's discuss transmitter part. So this part is basically, so if we consider x of 1 of t, x2 of t, the analog messages. So take the analog message and then the product modulator, the input of the product modulator is one is the analog message x1t and the other one is the carrier AC cos omega ct. But if we have a digital data, so after that we can use serial to parallel conversion, and then after that we are getting the digital to analog converter, and then after that we are getting x1 and x2t. This is the upper arm, so upper modulator, and then we are giving AC cos omega ct, and then we are getting double sideband suppressed carrier y2t, and then we pass the same carrier through the 90-degree phase shifter, and then we are getting AC sin omega ct and product modulator, and then x2t, and then on the other arm we are getting double sideband suppressed carrier signal. So y1t, so y1t is equals to the product of x1t and AC cos omega ct, x1t and multiplied by AC cos omega ct. Similarly y2t is the product of x2t and AC sin omega ct. So x2t and x2t multiplied by AC sin omega ct. And then at the output we are going to add them together, like we are just adding both of them, and then you will end up with the quadrature amplitude modulated signal, which is the upper arm. So and the second one is the quadrature, so quadrature to each other. So x1t AC cos omega ct plus x2t AC sin omega ct. So we are getting double sideband suppressed carrier on both of them. So the benefit is that you are going to transmit two double sideband suppressed carrier over the same bandwidth. So that is the benefit of using a quadrature amplitude modulator. So let's talk about the receiver. So on the receiving side you are having the input of quadrature amplitude modulated signal. So quadrature amplitude modulated signal. So you are giving the quadrature amplitude modulated signal as an input to the product modulator on the upper arm, and as an input to the product modulator on the lower arm. But you are using because this is a coherent detection, so you can say the synchronous detection. So in case of synchronous detection you are using locally generated synchronized carrier. So the same carrier AC cos omega ct, that is also the input of the product modulator, and then after taking the 90-degree phase shift you are getting AC sin omega ct. So the upper arm you are getting y1 bar t, the output of the product modulator, and after that you are passing that output through the low pass filter whose frequency is whose center frequency is f of m, and then at the end you will get first component z1, which is equals to half AC square x1t. So that was the transmitted message that you have recovered. So let's do analysis that how is it possible. So do some analysis. So y1 bar t, so y1 bar t is equals to the product of the amplitude modulated signal and the AC cos omega ct. So QAM signal multiplied by AC cos omega ct. You can have cos omega ct only, that is also good. You can have AC cos omega ct, that is also not a problem. So let's suppose we are having AC cos omega ct. So AC cos omega ct. So what is QAM? x1t AC cos omega ct plus x2 AC sin omega ct, and then multiply it with AC cos omega ct. So if you multiply the outer with the inner, then you will end up AC square x1t cos square omega ct, and then AC square x2t sine omega ct and then cos omega ct. We know the trigonometric functions. Cos square omega ct is equals to half of 1 plus cos 2 omega ct, and 2 sine omega ct and cos omega ct is equals to sine 2 omega ct. So this is cos square theta is equals to half 1 plus cos 2 theta. So this is 2 cos A cos B. So 2 cos A cos B is equals to sine 2A. No, sorry. So this is 2 sine A cos A. Okay. The angle is same, only the sinusoidals are different. Like 2 sine A cos A. So 2 sine A cos A will be equals to sine 2A. Okay. So that is why it is sine 2 omega ct. So using these two formulas in this equation, and then we will end up here AC square divided by 2x1 t 1 plus cos 2 omega ct plus AC square divided by 2 is x2t into sine 2 omega ct. So again you are going to multiply this with that one. So if you multiply this with 1, the answer is AC square by 2 x1t plus AC square by 2 x1t cos 2 omega ct plus AC square by 2 x2 sine 2 omega ct. So like if you draw the spectrum of this diagram, so you can see that, okay, so this is the spectrum of FM, so that signal, so that is the spectrum of the other one, so that is again 2fc plus minus fm. So it means that after passing the signal through the low pass filter, so this will allow, like this will, the frequency of that is fm and the frequency of that is 2fc plus minus fm. So it is fine that there is a sign but frequency doesn't change. Okay, frequency remains same, sinusoidals are changes but the frequency will not change. So that is why its frequency is also 2fc plus fm and its frequency is 2fc plus minus fm, but the frequency of the low pass filter is fm, the cutoff frequency is fm. So that is why only that signal can be passed through the low pass filter and the others will block. So after the low pass filter, you are having Z1t is equals to AC square by 2 x1t. So you can do the same analysis for this ohm as well. So for that one you can write Y2 bar t is equals to the product of the QAM and the AC sine omega ct, and then I hope you will end up with this formula. So let's talk about the constellation diagram. So we can have 4 QAM, we can have but we are looking for this 16 QAM so that we can better see the difference. So let's suppose we have 16 QAM. 16 QAM means 4 constellation point, 1 2 3 4 in each quadrant, 1 2 3 4 3 4 1 2 3 4, and then you can represent the distance, like you can represent the distance for each of the constellation point. Like for this constellation point you have distance d3, and then from here to here you have d1, and then from here to here you have d2, and then from here to here you also have d2. So what does that mean? Like you are changing the amplitude, the phase is going to be changed. So that is why you can say that 16 QAM is the combination of the amplitude modulation and the phase. So from this constellation point you can say that you are having 3 distance level, d1, d2 and then d3. So you are transmitting 2 bits in one symbol, like x1 is 2 bits, x2 is 2 bits, and overall you are transmitting 4 bits in one symbol if you are using 16 QAM. So let's discuss about the benefits of the quadrature amplitude modulation, that you are transmitting more bits per symbol. Like if you are sending more and more bits per symbol, so it means that you are increasing the data rate. So your data rate is increased. The second, you are transmitting more bits through the same bandwidth. You are transmitting all the signals using the same bandwidth, so it means that it is band efficient as well. Now discuss about the limitations. So QAM is susceptible to noise. So like noise can easily be attacked to the QAM signal. So that is why this is the limitation of the QAM signal. The second limitation is the coherent detection or synchronous detection, that you have to use synchronous detection only for the case of QAM. So it means that you are generating the local carrier signal which should be synchronized with the transmitted carrier signal. But in case if your locally generated carrier is not synchronized, I means that if there is a frequency or phase drift, then you will get some errors in the output signal. So this is also not good. So the third limitation is the power inefficient, because you are using linear amplifier, so that is why this type of modulation is power inefficient. So application for that one, you can use the QAM for the terrestrial digital TV broadcasting signal. So that's all. I think you have understood the quadrature amplitude modulation. So, but if you still have any question, you are most welcome. You can write your question in the comment box and we will try our best to answer your questions. Thank you for watching the video.